Today we're going to extend that to look at what happens when we graph 1 over sine, 1 over cos, and 1 over tangent. So it's the exact same thing that we did the other day, except our starting graph is going to be whatever the bottom was. So if we're going to graph cosecant, we're going to graph 1 over sine. So we graph sine first.
Is it going to be a pre-quiz online for the quiz?
No, yes. I haven't put that up yet, so I will put up that pre-quiz today. So we're going to draw, for cosecant, we're going to draw sine first, and I've already got that drawn for you at the bottom of your page. Then you're going to go through the steps. So how do we go through the steps for reciprocal? What's the very first thing that we did? We looked for our x-intercepts, and wherever there were x-intercepts, we drew asymptotes. So we're going to have a lot of them. So draw an asymptote at each x-intercept. And you can label them all. So we have vertical asymptotes wherever we have x-intercepts. You don't have one of these?
Yeah, I leave it.
There you go. Will we have an asymptote at y equals 0? No, not in this case. We have that asymptote at y equals 0 if our graph goes up to infinity or down to negative infinity, but our graph stops at 1. A sine graph never goes higher than 1, never goes less than negative 1. So the next thing you can do is graph some points. Well, what's going to happen right here at that maximum point? If we labeled that point, we would know that that's at pi over 2 comma 1. The only thing that changes with reciprocal is your y value becomes 1 over y. So that point's going to stay the same. Does that make sense? Same thing with this point, and this point. What's going to happen to this point down here? This is at 3 pi over 2 comma negative 1. It's going to stay the same. In fact, all of these minimum points are going to stay the same. Can you tell me from your unit circle another point on your sine graph? Other than those green dots that we've done so far, can you tell me another point on your sine graph? Okay, pi over 4 root 2 over 2. Do you know any other ones that are nicer numbers? What's this point right there? That's a nice number without square roots. Something 1/2. What is it 1/2? Pi over 6. Because sine of pi over 6 is 1/2. Where's that point going to go when you do the reciprocal? The x-coordinate's not going to change. It's still going to be pi over 6, but it's going to be comma. All you do with your y-coordinate is do 1 over y. It's going to be 2. So when you have fractions, fractions just become the reciprocal. So 1 over 2 becomes 2 over 1. you have enough to draw the entire graph. We see in this first section that this would have to go up like this. Can you see that it would have to go up in the other direction as well? Because over here, you'd have 5 pi over 6 comma 1/2. So it would become 2. And in fact, all of these sections, whoa, that's not green. All of these sections would be the same. What's going to happen on the bottom halves? Same idea. One of the things we talked about the other day is that in a section, whatever is the minimum of your original graph becomes a maximum of your reciprocal graph. Or whatever is a maximum of your original graph becomes a minimum of your reciprocal graph. So this point right here, that point in that little section is a maximum on our original graph. And it becomes a minimum on our reciprocal graph. So all of these asymptotes and all of those green lines together, that is the graph of cosecant. We've labeled our asymptotes. We found some points so that we could draw it. And then we graphed cosecant. What I'd like you to do is do secant. How did you do? Did you get your asymptotes? Did you label them? First one is at pi over 2, then 3 pi over 2, then 5 pi over 2, then 7 pi over 2, and same thing in this, just with a negative. There's our asymptotes. And same thing as with cosecant, these points would stay the same on top and bottom. Top sections and it would look like that. Now, an interesting thing happens with cotangent. Yeah. So first of all, wherever you have x-intercepts, this one you'll want to use colored pen other than gray or black so that you can tell the difference. There's going to be a lot of lines on here when we're done. I know. So after drawing all of these asymptotes, and they're going to be at x equals 0, x equals pi, x equals 2 pi, x equals 3 pi, and the negatives. Now, technically, the tangent graph goes up forever. So according to our notes before, when your graph goes up forever, you will have an asymptote at y equals 0. But this is where tangent's a little bit different because this is where cotangent's a little bit different because it depends on what your definition of cotangent is. We know that cotangent's 1 over tan. We also know that cotangent is what over what? cos over sine, right? So because it's cos over sine and 1 over tan, there's discrepancies in the graph. Because if you were graphing 1 over tan, you would have an asymptote at y equals 0. But if you're graphing cos over sine, then this value that was originally an asymptote is actually allowed. Because this value right here where the asymptote crosses, those are all places where sine of theta is either 1 or negative 1. And so it's actually not a non-permissible value. And those are all places where cos of theta is equal to 0. Okay? Because if you think about tan of theta is equal to sine of theta over cos of theta, right? So wherever you have asymptotes on that tan graph, that's where cos was 0. But when you do the reciprocal of that, and if you think of cotangent as cos over sine, wherever cos is 0, cotangent is 0. So these blue points are actually part of the cos graph. What happens at pi over 4 for tan? What's tan of pi over 4? It's 1. So if I put that point on here, that would be pi over 4 comma 1. Can you see that that point is also on cotangent? Because if you did 1 over 1, that would stay the same. So in fact, we can go across and do all of those points that are going to stay the same at 1. What's another point that's going to stay the same? At negative 1. All the points that are at negative 1 are going to stay the same. So now we've got points that are 1 and negative 1 staying the same, and we do have this point at the asymptotes before, which will be 0. Your cotangent graph looks like a tangent graph going the other way. So you just have to draw towards the asymptotes. Whoop. And so that blue graph is our cotangent graph. Now what we're going to do to end is we're going to go back to each of our graphs, and we are going to characterize them. We're going to say what the domain, range, y-intercept, zeros, period, and I'll teach you what odd and even means. So here's our first one for cosecant x. The domain is everything except x can't equal what? A lot of asymptotes, right? X can't equal 0, pi, 2 pi, 3 pi, 4 pi, 5 pi, 6 pi, 7 pi, 8 pi, 9 pi. Just keep writing them. Or k pi, where k is an integer. Nice. Our range for cosecant. Okay. Y is greater than or equal to 1, or y is less than or equal to -1. If you were doing this in interval notation, you always start from your smallest values. Is there a smallest value? No, so you'd start at -infinity. And it goes until it gets to -1, and since -1 is included, you have a square bracket. Or, this is a symbol for or, it starts again at 1, including 1, and goes up forever to infinity. So you could write it either in set notation or interval notation. So we've done domain and range. Y-intercepts. Does it have any y-intercepts? No. There are none. What about x-intercepts? Does it have any x-intercepts? No. There's none. That's pretty nice. Equations of asymptotes. Yes, we do have asymptotes. The equations of the asymptotes are all x equals k pi. Almost identical to the domain, right? But in the domain we say x can't equal. When we say the equations of asymptotes, we say x equals k pi, where k is an integer. Does it have, what is the period? How long does it take cosecant to repeat itself? It takes the same amount of time to repeat itself as sine does. Its period is 2 pi. Now, cosecant is an odd function. I'm going to quickly give you the definition of what odd and even functions are. It's pretty easy to understand what they are if you think of x squared, x to the 4, and x to the 6 have even exponents. And an even function is when it's symmetrical about the y-axis. If you can flip something over the y-axis once, it makes it an even function. Odd functions, like x cubed, x to the 5, x to the 7, and so on, if you think of an x cubed graph, what is in the top right-hand corner gets flipped over once and then flipped over again. It gets flipped twice. That makes it odd. Can you see for cosecant, if I would take this part right here, if I would flip it over the y, it would go over here. And then if I would flip it down, it would end up right there. Can you see that double flip? If you flip it over the y and then over the x, it matches up perfectly with what it has on the other side. That's what makes it an odd function. If we go to secant, could you do domain, range, everything for cosecant? Could you do the same thing for cotangent? That's your homework in this section.